This is the fourth, and I'm sure you'll be pleased to hear, the final part in a series of videos in which I've been presenting Ferroresonant Transformers. And in the previous videos I've been demonstrating the performance of this particular transformer, attempting to explain how it works. It is fairly complex, so I've been going through it step by step, and up to this point we've gone through the general operation of the transformer and looked at a couple of the waveforms. So in the last video we looked at the input voltage waveform and the current waveform going into and out of the resonant circuit. That's the resonant winding and the resonant capacitor. So if I turn the power on, we'll have another look at that, and you can see on the scope that what we have are the first trace, which is the blue trace, is the voltage input waveform, and the yellow trace is the resonant waveform in the resonant circuit. So that's the current in the resonant circuit. And if I adjust the load, you'll see that the phase relationship between those two is modified. Okay, and that's as far as I went in the previous video. Now, what we'll look at now is the current waveform of the primary winding on the transformer. Now, of course, it's the current in the winding that dictates what the flux in the transformer core is doing. And because it's the flux that is used to excite the resonance coil, then that is what we're really interested in, because that is what dictates what the resonant circuit and hence what the output of the transformer will be doing. So what should be happening is, as the voltage waveform rises on the input to the transformer, at a certain point we should reach a discontinuity between the increasing voltage of the secondary winding, and that includes the resonant winding, and the resonant circuit itself. In other words, the circuit should start to rise in a non-proportional way compared to the input voltage, and that's the resonance of the transformer coming into effect, or the resonance of the resonant winding and capacitor coming into effect. And that sudden increase in current, and that's what we're seeing in the yellow trace, is what causes the local saturation in the secondary part of the core, and that in turn is what gives us our regulation. Now, in this video what I want to do is explain how the actual regulation mechanism works. But before we'll do that, we'll have a quick look at the current waveform, just to further clarify that it's the current in the primary winding that really drives all this. Now, in the comments of the previous video I was asked whether these are any good. So this is a current clamp that's designed to plug into a scope, and the answer is yes, they're quite useful, and the only thing is they're relatively expensive for what they are. I use them now and again if I want a means to take calibrated readings of currents flowing through conductors. They only work up to about 20 kilohertz, but you can use something else if you want that's much cheaper. You can just get hold of something like this. This is of course just a split core current transformer. These are about 1/10 of the price of one of these, but we'll do the same thing. It's just not calibrated in the same way, and it's not as sensitive, but it will work just as well. So what I'm going to do here, because I need two current clamps, I'm going to leave this one on the resonant circuit, and I'm going to attach this one so that it's reading the current flowing through the primary winding. So I'll just turn the power off. We'll disconnect the scope from the mains input, and as I said in the previous video, if you do connect your scope to the mains, be extremely careful. I do not have this connected direct to the mains. I've made an isolation and dropper circuit, but if you have a differential probe or something like that that's isolated, that will obviously work far better. But this will work in the arrangement I have. Just be very careful if you start doing something like that. Okay, what I'm going to do now is clip this around the input to the primary, and what I can do now is just attach the scope across the output of that. Okay, so now we're going to be taking two current readings. We're going to be looking at the current in the primary winding, and that will be the blue trace, and then the yellow trace is still going to be the current in the resonant circuit. So I'll turn the power back on. We will need to change the scope setting. So as you can see now, what's happening here is as the current in the primary starts to ramp up, so we're getting to a point where the resonant circuit kicks in. And it's very clear that there's a certain point in both directions. So in both the positive and negative half of the main cycle, we're seeing the same thing. So it's pretty much at the same point. So if you look at it, this point here, you'll see that at a certain point in this waveform we're hitting the resonant part of the performance of the core, and if we look at the other half phase, it's pretty much a mirror image in terms of the point at which the resonant kicks in. And that's what's happening, but because these are now tied together, so the current in the primary, which is the blue, and the yellow are tied together, they're interdependent, so or at least the yellow is dependent on the blue, then the phase should stay the same even if I change the load. So if I start changing the load, you'll see that the phase relationship will stay pretty much the same. So the amplitude is changing, but the phase is staying pretty much the same. So what we're seeing here is that as the current in the primary rises, at a certain point we reach resonance in the secondary part of the transformer. We get a sudden increase in the current in the second part of the transformer, in the secondary winding, the resonant winding, and that sudden increase in the current causes a sudden increase in the flux in the second part of the transformer, the secondary part of the transformer, and that pushes the secondary part of the transformer core into saturation. So the next question is, why do we want to do that? What's the advantage of pushing part of the transformer core into saturation? The primary, I should stress here, does not run into saturation. It's important that it doesn't run into saturation for the same reason you don't run the primary into saturation on a standard transformer. So what we'll look at for the rest of this video is why we want to push part of the transformer core into saturation. What advantage does it give us? So what I'm going to do to try and explain this is get this out of the way, and we'll have a quick look at a standard transformer. One thing I'll do as part of a clue, I've given this clue in a previous video, but I'll give it again here so you can try and work this out as we go through this video. If we look at the voltage across the transformer, this is the secondary, I've got the meter set to AC. This is a true RMS reading meter, and that's quite important. And our output voltage is about 47.6 volts DC, so that's after rectification and after smoothing. But if I look at the AC side of the secondary, we're seeing we're getting 45 volts, or 45.3. So we've got 45.3 volts AC and 47.6 volts after we've rectified and smoothed it. So huge clue there as to how this actually works. But what I'll do now is go through and try and explain exactly what's going on with this transformer that gives us this good self-stability, self-regulation. Okay, so what I have set up here is a standard transformer. This is just a standard ordinary toroidal transformer. It's about 9 volt secondary, 240 volt primary. It's connected to a bridge rectifier, smoothing capacitor, and then the output of that is connected to the electronic load. So looking at the multimeter, if I measure the AC voltage going into the rectifier, we're getting 10.8 volts. And if I switch to DC and we look at the DC voltage across the capacitor, this is after rectification and smoothing, we're getting 13.3 volts. Now, This is kind of a big clue that I gave a few minutes ago, and it is very different from how the Ferroresonant Transformer works. So if we start with the AC voltage that's on the secondary of the transformer, and that's 10.8 volts. So if we take a calculator and we start with 10.8, we'll multiply this by 1.4. So 1.4 is just the rule of thumb conversion to convert AC into rectified and smoothed DC. That gives us 15.12, and then we have to subtract from this the voltage drop in the rectifier. It's full wave bridge rectifier, so we have 2 diodes in each half phase, and we're getting about 1 volt or so drop in each diode. So we need to subtract probably a little under 2 volts from this. So if we subtract 1.8, that's the voltage that we expect to see coming out of this system in DC, and that's pretty much exactly what we're seeing on the electronic load. It's reading just over 13.3. So this all works, but more importantly, if we look at the scope is showing the waveform of the AC coming out of the transformer. So the waveform going in will be the same as we had with the Ferroresonant Transformer, it'll just be mains. But this is the waveform that we're seeing coming out. So a few important things here. Firstly, as I vary the mains voltage, you'll see that the voltage on the secondary, so the blue trace, varies in direct proportion to the incoming mains voltage. In fact, I'll just connect the multimeter across the secondary so you can see exactly what the voltage is. So I now have the multimeter connected directly across the secondary of the transformer, and I'll start to vary the mains. The AC coming out of the transformer is currently 10.5. I'll change the mains voltage to 120. So around 120, we've gone from 10.5 to 5.3. So we've halved the mains voltage, and the AC voltage coming out of the transformer has also halved. And it will do this all the way up and down. It's ratiometric, so the voltage coming out of the transformer will be in direct proportion to the voltage that we feed into it, and that's the basis of how transformers work. It's just a ratio between the primary and secondary based on the ratio of the number of turns on the primary and secondary. There are other factors that make a minor difference, current and resistance, loading, that sort of thing. But basically the output voltage is a ratio of the input voltage dictated by the ratio of the turns on the transformer. So as you can see, the waveform is also a sine wave, so it tracks the mains voltage as well. So the mains voltage we're feeding in is of course a sine wave, and we're getting a sine wave out, and it doesn't make any difference what amplitude of voltage we put in, we're getting a sine wave out. Okay, so bearing this in mind, we'll go back to the Ferroresonant Transformer. Of course, this change in voltage with a change in input voltage means there's no inherent regulation with this standard type of transformer. The output voltage will just be dictated by whatever the input voltage is. If the input voltage halves, so will the output voltage. If the input voltage doubles, then so will the output voltage. Okay, we'll go back to the Ferroresonant Transformer and see how it differs. Okay, we're looking back at the Ferroresonant Transformer. I've got it hooked up in exactly the same way I did before, except that I now have the scope looking at the output waveform of the secondary. The multimeter is set to AC, and it is connected to the AC output of the secondary as well. So the waveform we'll be looking at on the scope is actually the output waveform of the secondary of the transformer. And this is where you'll start to see the real purpose of the ferroresonance system. So if you recall, a few minutes ago we looked at the standard transformer, and we saw how the secondary voltage was a sine wave that was in direct proportion in terms of its amplitude to the input primary voltage. But if you look at the waveform on this transformer, so I'll now turn it on, you'll see that what we're actually looking at is what appears to be a very heavily clipped sine wave. So if you see this in an audio amplifier, you'll recognize this as severe clipping. And it's exactly the same principle, and that's how this transformer works. The secondary is trying to increase its voltage beyond the voltage we actually want. And because we are forcing the core into saturation, then what happens is the output voltage will continue to rise from the secondary until the core that the secondary winding is sitting on runs into saturation. When that part of the core runs into saturation, then the output voltage from the secondary winding will stop increasing. It can't increase any further because the core is saturated. That is, the magnetic flux cannot increase anymore. And because the magnetic flux cannot increase anymore, then the resultant voltage induced in the winding that's on it cannot increase any further either. And so what's happening here is the secondary part of the core is being forced into saturation very early on in the primary voltage cycle, and that means that it's kind of running straight up into the saturation region. It reaches its peak voltage very early on, and the result there is that the voltage, the AC voltage, is limited to a value dependent on the design of the transformer. So in this case it's limited to around 45 volts, and that 45 volt limitation is because to go above that the core flux would have to rise further, and of course the core flux cannot rise further because the core is saturated. So if I start to reduce the primary voltage, then all's going to happen here is the point at which we run into secondary saturation is going to change, and that's where we saw the phase relationship between the primary voltage and the resonant circuit current changing. So I'll start to reduce it. You'll see that nothing really changes much on the output waveform. It's staying pretty much the same. All that's really happening is the sides of the rising and falling edges are becoming less steep because we're not running quite as far into saturation, so to speak, and that means the core is not saturated for quite as long in the cycle. So I'll continue to go down, but you'll see beyond a certain point we'll go out of this resonant operation of the core and we'll actually turn back into what amounts to a sine wave. But as we go up, we reach the saturation point, so it's now starting to, well, it's now not working as a proper ferroresonant transformer, but as we start to go back up we reach the point where the core is saturated, which is about there, and if we continue to go up, the output voltage cannot continue to rise much further because the core in the secondary region is fully saturated, and so the transformer can't give a higher voltage output than that. So that's about 160 volts we reached that point. I'll keep going up, so we're now at 190 volts, but you can see that all that's happening is we're just running into saturation slightly sooner, but the actual output voltage is staying the same because the transformer is not able to provide a higher voltage than that. Okay, well I hope that makes sense. As I say, just to recap, the transformer works by running the primary in the linear part of the flux curve. The secondary part of the transformer core is driven into saturation through the use of a resonant winding and capacitor circuit. That resonant circuit causes the secondary part of the core only to run into saturation. The two parts of the core, the primary and secondary, are partly isolated through the use of magnetic shunts, and that allows only the secondary part of the core to run into saturation. And by allowing the secondary part of the core to run into saturation, we limit the voltage it's able to produce. And so if we increase the load, for example, all we're really doing is pulling down what would have been the peak value but we're not of course reaching the peak value because the core saturation is limiting that. And if the load reduces, then the reverse happens. We just run into saturation earlier in the current cycle of the primary. Okay, I hope that makes sense. That's the last in this series on ferroresonant transformers. If you do want me to go into more detail on these, then let me know. I'll look into posting some more videos. But hopefully this has gone some way to explain the basics of how these devices work. I've kept it very simple. There are many different versions of ferroresonant transformers. Some have additional windings that are used to further help with regulation, but this is the basics of how they all work, and hopefully you've found these few videos of some interest.